Okay, we have our another integral. This one sent to me by Lemon. We have the integral from 0 to 1 of x ln x all to the n dx. And I have this condition on it that we want n to be a member of the positive integers. And then this is a little bit different than the problem he sent to me, but I wanted to do the definite integral just because it's going to simplify a little bit easier. So to get started with this, I'm going to want to do a U-substitution. Now you could do it two different ways that I know of anyway. You could do this with integration by parts. I think I did that. I think I did something really similar with integration by parts not too long ago. So today I'm going to do it with the gamma function. I'm just going to distribute the power into the x to the n here and separate this like this. And then for the U-substitution, I'm just going to do my U-substitution on natural log x for now. So we'll see if we do u equal to ln x. Let's also get a value for x to get the dx value. So like rearranging this with log properties, we'll have x equal to e to the u. Take a derivative on this. Now for our dx value, that's just going to be e to the u du. So go ahead and substitute. First, take 1. We'll plug in 1. Natural log of 1 is just 0. Then looking at 0, natural log of 0, that's going to happen when we're going to minus infinity. Now for x to the n, we can just take this, and if we raise both sides to the power of n, this is going to be the same thing as x to the n equal to e to the nu. So we'll write that in here as e nu. This thing is just our u, so we have u to the n, and our dx is this thing, eu du. But now we have the same base here and here, so let's combine these terms, just adding exponents. And then the thing I notice here is this is kind of starting to look like it's set up for the gamma function. We have a few problems. For the gamma function, we want this bound to be infinity. We want to actually swap them. For that, we want to go from 0 to infinity. And we don't really like this exponent here. We want this to be something, we'd like it to be like e to the minus u or e to the minus something. So what I want to do on this just to clean it up is let's just do another substitution. There might be a way to combine the substitutions, I'm not sure, but let's just do it like this. So what I want, for that n plus 1 minus u, I want that to become minus t. So we'll do something like we want n plus 1 times u to be minus t. And then I can solve for a value of u, just divide by n plus 1. So we'll have minus t over n plus 1. Take a derivative. du is going to be here just minus 1 over n plus 1 dt. So now just go ahead and substitute. Take the 0, plug a 0 in here. Our t value for the upper bound is going to be 0 still. Plug in minus infinity. You could rearrange this and bring the minus on the other side. We're assuming that n's a positive integer. That's going to be important here, right, when we determine this bound. Because n's positive, you put minus infinity in here with the minus. That's just going to turn this into a positive infinity. This here now is going to transform into e minus t. Our u value is all this, so we're going to have minus t over n plus 1 all to the n. I'm going to clean that up in a minute. For du, this part's a constant, so let's just bring that up front. So we'll have minus 1 over n plus 1, and then we just have our dt. Then from here, what I want to do is clean up this bit right here. And actually, before I do that, let's use this minus sign. Because I want, like I said, for the gamma function, we're going to want it the other way, and the minus sign I can use to flip the bound. So we'll use this and flip these around. And then over here, I want to distribute the exponent into everything. Look at this like a minus 1, distribute in that, distribute the n into the denominator. When you do that in the denominator, this is going to become n plus 1 to the n. Combine it here, look at this like n plus 1 to the 1. This is going to become n plus 1 to the n plus 1. And now that we have this all split up, this piece right here, minus 1 to the n, that's just a constant. So let's bring that out front of the integral here. And now we pretty much have this set up to use the gamma function, but I need to do one thing. This exponent should be something minus 1. So in order to kind of create a minus 1 on here, we can write this as n plus 1 and then subtract 1. That way we just added 0 to it. So then we have our input here for the gamma function. And then this whole thing here, this is just going to become our gamma of n plus 1. And now we can take what we have in front and combine it with our gamma of n plus 1. And what we can do is write this as minus 1 to the n over n plus 1 to the n plus 1 times gamma of n plus 1. And then this is a fine solution, but then let's also look at this a different way. We have the gamma function, and we have this formula that we can write for gamma of n plus 1. This can be written as n factorial. There's no trouble expressing this as a factorial. We've defined this to be positive integers, so I can also write this solution as minus 1 to the n n factorial over n plus 1 to the n plus 1. Then one note on this, we weren't really required to have this restriction because the gamma function, if we leave it this way, the gamma function is defined for non-integer values. It still has some restrictions on non-negative integers. But if we want to, we could drop this restriction and put some looser restriction on it. Okay, thanks to Lemon for the problem. Thanks everyone for watching today. Have a good day.